Hi everyone. One of the laws that we derived earlier, but haven't had a chance to practice with yet, is Avogadro's law. And so Avogadro's law allows us to relate the volume of any gas at a standard temperature and pressure, or a constant temperature and pressure, to the number of moles of that gas. So we're going to get some practice with Avogadro's law, and we're also going to apply some gas density here. So there's some fun things you can do where we can plug in basically an amount for N that is based on the molar mass and the mass of a gas. And because density is mass over volume, where m is the mass, then we can eventually get out to a gas density that looks like this. So we'll practice deriving this in class because it's a little bit of a longer derivation. But end result is we can talk about the density of a gas being equal to its molar mass. So m here is the molar mass, times its pressure over that same R value that we've been using, times temperature. And one little note, we're going to use D for density here for clarity and lack of confusion. But it turns out if you go onto like a college level course, oftentimes the Greek letter rho is subbed in for density. So we're just using D to kind of avoid confusion. But if you ever see the Greek letter rho, that also means density. So let's get some practice. I've again defined our variables for the sake of time. In number one, you'll notice that you pull out a number of moles, and that we'll call N1. We have an initial volume, and we have a final volume. We are interested in solving for our final number of moles. So we're going to use that Avogadro's law, that V1 over N1 being equal to V2 over N2. And you'll notice in this case that we want to solve for N2. And so you can cross multiply and divide, you can do whatever you'd like to do to solve for N2, but ultimately we should end up with this. We should end up with V2 times N1 over V1 as our N2. And if we plug everything in, then our N2 is going to be equal to, our second volume was 16.5 liters, times our initial number of moles, which was 1.5 moles, over our initial volume, which was 36.7 liters. And when you do that, you'll notice that your liters conveniently cancel. You have 2 sig figs, 3 sig figs, and 3 sig figs. So your answer should have 2 sig figs, and our answer will become 0.67 moles. So basically what we're saying is if we have two gases under similar conditions of temperature and pressure, if you have 36 liters of a gas, then you have 1.5 moles of it, but if you have a lot less of the gas, if you only have 16.5 liters of it, then you only have 0.67 moles of the same gas, which in this case is nitrogen. All right, let's try a different one with helium. So again, we have an N1 and a V1 and an N2 and a V2. So again, we're going to use Avogadro's law, which is V1 over N1 equals V2 over N2. We're going to rearrange for the variable that we're interested in, which is V2. So to get V2 by itself, we need to multiply out N2. So that's V1 times N2 over N1. We can plug everything in, so that initial volume that we had was equal to 2.35 liters. We're going to multiply that times our second molarity, or our final molarity, which was 0.337. And we'll put that over our initial molarity, which was 0.105 moles. So that will allow us to say that our final volume, if you cancel everything out in terms of moles, and you look at your sig figs, every one of those numbers has 3 sig figs. Our final volume, therefore, is 7.54 liters. So Avogadro's law, very much in the same vein as the other laws we've done. We just wanted to split it up for sake of clarity. Let's talk about that gas density equation, so that D equals MP over RT, and that's a little bit different. Unrelated to Avogadro's law, it honestly looks a bit more like the ideal gas law, because you'll notice when you define your variables for number 3, you get this. So I've already done some work here. Let's talk through what we've done. You'll notice that the density is unknown, The molar mass, we are told, is 39.95. Now, we're not actually given the molar mass in the problem, but we are told that we're dealing with argon. Argon is a gas on the periodic table. You can look up its molar mass, and you'll find that its molar mass is 39.95. And remember the units, grams per mole. So we want to make sure we have all of our units involved here. Pressure was given in torr, but remember that our R value is given in units of ATM. So that's why I've converted that pressure to ATM so that we can use the R value, because part of D equals MP over RT is indeed the R value. And of course, I've converted temperature to Kelvin. So we are using density is equal to MP over RT. That's our new equation. When we plug things in here, we are solving for density. So the molar mass in the problem is 39.95, and remember that's grams per mole. We're going to multiply that by the pressure, which is 0.725 ATM. And all of that is going over, first off, our R value, which remember has some crazy units. So the R value is 0.0821 liters times atmospheres over moles times Kelvin. And that's getting multiplied by our temperature, which is 298 Kelvin. Okay, so we have a lot going on there, but let's check out what cancels. So in the numerator, there's an ATM. In the denominator, there's an ATM. In the denominator only, there's a Kelvin, and there's a Kelvin. In the denominator of the top and the denominator of the bottom, so those will cancel, we have moles, and we are left with grams over liters. But remember what we're solving for. We are solving for a density. And so density is mass over volume. We need 3 sig figs. We get 1.18. And the fact that we have grams over liters as our uncanceled units is really good because it's a mass over a volume, which indeed is a density for that gas. Let's try one more application. So here is in number 4 a problem where we're given a density, but we want to solve for molar mass. And so we again have this equation that's D equals MP over RT. But now we want to solve for molar mass. So how would we do that? Well, we'd multiply RT up, we'd divide out P. So we would get that the molar mass is equal to dRT, looks like dirt, over pressure. And so we can plug everything in, right? We know that our molar mass then is equal to, keep your units, 2.0 grams per liter, that was the given density, times our R value, which is 0.0821, because we want the ATM R value, so liters ATM over moles times Kelvin. And then we're going to multiply that times the temperature, which initially was or is 300 Kelvin. And then we'll divide this whole thing by our pressure, which we said was 1.50 ATM. And again, let's look carefully at our units. So unit-wise, Kelvin, in the numerator, we have Kelvin on the top, Kelvin on the bottom. In the top, very top, we have ATM here. In the numerator, again, we have liters on top here and liters on the bottom here. So those cancel out. So ultimately, we're left with grams per mole, right? And so our molar mass becomes a number of grams per mole. And we need 2 sig figs from the 2.0, so we will get 33 grams for every 1 mole.